Okay, today we are doing set 5, as I've already mentioned. Okay, this is the worksheet. As what we're going to focus on today, right, are the 2022 prelim questions, which are towards the back. So the first couple of questions on the 2018 questions, right, we'll probably not be doing it in class today, lah. Okay, you guys go and try all these yourself, right? Go flip over to like question 5. Yeah, this one. Okay, we'll be focusing on the 2022 questions only today, lah. Right? So flip over to question 5 and I'll tell you guys what to do. Okay, I want you guys to do part A and part B only. Okay, we do just this chunk first, right? So it's about okay, it's about 10 marks. Okay, I'll give you guys about 12 minutes, okay, to finish this up, lah. Right? Okay, so 12 minutes for 5A and 5B. Okay, I'll time you guys. We start now. Maybe 5 minutes left. Okay, 2 minutes left. Okay, time's up. All right, let's go over the answers. Okay, overall, this question, I think it's the second part, part B, right? Okay, that's a little bit tricky, right? Let's take a look at part A first. I don't think there's much for me to talk about for part A, right? I mean, it's just a definition plus a bit of explanation, right? Just go and check your answer, okay? Because this question, part 2, right? Usually they give 3 marks for explaining the color alone. But they only give 2 marks over here, and they want another 1 mark, right, on why the color changes. And you shouldn't just briefly mention also, okay, go and explain a little bit more. Okay, so let me just highlight on what's important. Okay, this entire first half, right, I'm not gonna touch on it because it's just a template answer at this point, right? Okay, but the second part over here, first of all, they mention the word equals. Okay, when they mention aqueous, okay, clearly we are looking at nickel surrounded by 6 water molecules. And then when you add ammonia, there is a ligand exchange reaction, and you should mention that in your answer as well. Okay, even though it's not the central idea of the answer, it is still necessary. Okay, so ligand exchange is number 1. And the second thing is ligands are the sole reason why you have different colors in the first place. Okay, because ligands split the d orbitals to different extents, okay, giving different energy gaps. Okay, so you must talk about splitting d orbitals and different energy gaps. Okay, that is the main focus, right, when it comes to why ligands give different colors. Right, you must have these 3 keywords in order to get the 1 mark. So this third mark over here is not easy to get, but just make sure you write all keywords in your answer next time, then you will be safe. Okay, shouldn't be an issue for this. I'm not going to flash this for very long also because you can just check the answer, right? Can now. Okay, I want to look at the second part of this question. Okay, a bit of energetics concepts here and there. But let's look at this first part. It's quite a demanding question alone, right? Because they're asking for 2 things. You need to explain large and positive. Okay, so I want you guys to not conflate both ideas together, because I think that's what some of you guys inevitably do. You kind of lump both things together, right? And the examiner can't give you both marks. Okay, you should explain them separately. Okay, make it very clear in your answer. Okay, so I'll show you the answer later. Okay, and then you will see how it's structured. But the easier part to explain first is positive. Okay, so why is it positive? Okay, I'm sure most of you guys can see. Okay, there is an increase in number of aqueous particles. Okay, so quite clearly from 4 on the left to 7 on the right. Okay, increase in particles, increase in number of ways to distribute the particles. Okay, that is to explain positive. Okay, but to explain large, okay, you need to convey the idea of the magnitude of the entropy. There's a huge increase. Okay, so why is there a huge increase? Okay, purely because of the 4 and 7, right? You might end up repeating your answer. Okay, I kind of get if you felt that way. Okay, but to avoid repeating your answer, right? Okay, you should kind of like phrase it slightly differently. Okay, so this is what we should be doing instead. This entire first part here, increase in number of ways to distribute particles. The increase here, right, already conveys the idea of positive entropy. Okay, and then the second part, right? Okay, yeah, I make it very clear to the examiner that I'm discussing the magnitude. Then I write the word magnitude in my answer. And that's because the amount of aqueous products is a lot more than the aqueous reactants. So I compare the right and the left. Okay, since the products is more than the reactants, okay, that conveys the idea of large magnitude. So try to distinguish your answer using these kinds of very helpful keywords now. Okay, such keywords can help the examiner to mark and give you the 1 mark each, okay, more easily. Okay, so just be very careful in the future. Don't lump both ideas together, because if not, they will treat it as just 1 point. Okay, so distinguish your answer carefully. Okay, so that's for the first part. Okay, second part, okay, delta G, I don't have to discuss this. You should be getting this 1 mark, like every single one of you guys. You should be getting this. Okay, shouldn't be an issue. Okay, but part 3 is quite an important question. Now, they normally like to link delta G and position of equilibrium together. Okay, even though one is energetics, one is equilibrium, it is linked together. Okay, everything is all okay together in this question. As you can see here, right? Okay, you must first convey the idea of spontaneity. I must see the word spontaneous in your answer at least once, right? Spontaneous means what? Okay, let's just be careful here. Because this is an equilibrium, right? You should make it clear that any delta G that you calculate, right? The forward reaction is the one that's spontaneous. From now on, just I know it's a you may not be wrong if you write spontaneous, but I just want you guys to clarify your answer in future. Okay, just to improve for your answer a bit. Okay, it's the forward reaction that's spontaneous, especially when you discuss equilibrium concepts. Okay, right? So let's take a look. Okay, so the forward reaction is spontaneous. Then you can infer the POE lies towards the right. Okay, and what does that mean about the ligand? Yeah, so we've discussed strength of ligands before. Coming back to this equation over here, we did explain that strong ligands will replace weak ligands, right? The stronger one will replace the weaker one. So in this case, right, if we can infer the POE is lying towards the right-hand side, we can see that this bidentate ligand wants to replace this weaker ligand, right? So that's why it successfully proceeds in the forward direction. However, okay, you can treat it as, if you don't really understand this, okay, just take a look at the opposite lah. Imagine the POE was lying towards the left, which means this part here predominates, right? That means ammonia ligand can be inferred to be stronger than the bidentate ligand, okay, which is not the case over here lah, okay, but depending on the forward and backward reaction, you can actually use this to identify which one is the stronger ligand. Okay, so you don't have to explain what I just said. You just need to infer because it's only 1 mark, right? Which ligand bonds preferentially? Okay, you can infer it's a stronger ligand. So you might want to mention that first. Okay, that's how it bonds preferentially. Okay, so ligand exchange, settle. Any questions so far? Okay, again, any questions, just unmute or just type in the chat. And just take note, when you type in the chat also, right? Okay, just type it in the all chat. Don't send me a direct message. Okay, so that everyone can see also. Okay. If there's nothing, I'm just gonna move on. Okay, coming to this last part, right? Okay, I think this is the part where some of you guys are struggling with. Okay, they are saying that bidentate ligands are faster than the monodentate ammonia ligand. Then they ask you to suggest why. Okay, I can tell you guys first that this 1 mark here is not worth it in exam. It's one of those 1 marks that are not worth it, and I need you guys to know when to not chase after these kind of marks in exam, especially if you don't have time. Okay, I'm just going to show you the answer, and you will see why it's a little bit demanding lah. Okay, here. Okay, so why is the bidentate ligand better, faster than the monodentate ligand? Okay, you read this first part first. Okay, then I explain what this means. Okay, some of you guys might understand what it means. Okay, but let me just briefly explain again. They are saying that the bidentate ligand, right, has 2 amines like that, right? Okay, that's how the ligand looks like. When you attach the first one to the central metal ion, it is intermolecular, correct? One molecule, another molecule, then it's across 2 different molecules. Okay, but when the first NH2 group has already been attached, now to attach the second guy, it is not an intermolecular reaction. Okay, it's happening within the same molecule because one side is attached already. I hope you can understand what they are trying to get at. Again, I don't expect any of you guys to be able to get this question to even, maybe if you even get the idea, I don't expect you guys to be able to explain it properly. Okay, it's not an easy question. Again, it's one of those where very open-ended. Okay, depending on your answer, they might give you the mark if you justify correctly. Okay, so that's the first one. Can see what's happening, right? Okay. The second answer is, again, this is not necessary for 1 mark, honestly, it's not worth it. Okay, but just take a look first. Okay, and yeah, okay, perhaps after scanning through this, they are saying this, okay, I can go back to the, okay, let me just go back to the, okay, so let's look at the equation here. Okay, now, the second reason to summarize, right, they're saying this, the bidentate ligand only requires 3, but the monodentate ligand requires 6. Now, 3 versus 6, there's a much higher chance, right, to collide 3 molecules successfully than to collide 6 molecules successfully. Okay, we learned the idea of effective collisions. right? Colliding 3 successfully has a way greater probability, right, than having to collide 6 successfully. That's what they're trying to say here. And if you write it in what I just mentioned, right, if you write exactly what I just said, okay, then fine. Okay, but the way they phrase it is very challenging lah. Okay, I don't expect you guys to use these kind of words. Sequential bimolecular reactions. Nah. Okay, whatever. Okay, so I suggest you guys, right, take note of the first. Okay, the first one. Because the first one is a lot easier to digest. And if this really does come out in exam again, right? Okay, I hope you guys can get this 1 mark lah. Okay, why are bidentate ligands? Okay, let me just. Why bidentate ligands faster than monodentate ligands? From now on, just remember this as your template answer. It doesn't have to be word for word. Just remember the word intermolecular and intramolecular, and you're settled already. Okay, we have a question in the chat. Okay, can I explain? With a higher probability of forming 1 inter than 1 intra than 2 inter. Okay, yeah, okay. Take a look at the answer in the chat. Okay, I think this is also another way to paraphrase the first answer. Okay, and it kind of lumps the second answer together also. Yeah, okay, I will accept this. Okay, you see, right? It doesn't have to be word for word. Okay, the same as the answer key. Okay, but I will accept that. In fact, I would think this is quite a good answer also. Yeah. Okay, any possible other answers you all want me to track? Okay, I mean, if you don't tell me, I also can't track now, right? Okay, so if no other questions, okay, I think so far the question has been quite kind, yeah, apart from that last portion. Okay, and I want you guys to complete part C. Okay, this one not very long lah. Okay, I'll give you guys about 6 minutes. Okay, I'll answer some more questions in the meantime. What's this? Okay, I have another question. Is it possible to say about availability of lone pair? That was initially my first answer. Okay, so some of you guys are saying, I want to discuss this actually. What is it? Okay, over here, right? Okay, so most of you guys might have come up with availability of lone pair because the fact is this bidentate ligand, right, has a electron donating alkyl group, and the electron donating alkyl group will make the lone pair more available. Honestly speaking, right, I was curious. I was actually, kind of questioning why this wasn't the answer. Like it wasn't even part of the answer key. Yeah, okay, but I would say this is a possible answer actually. In fact, it does make some sense. So there's no basis for me to reject this answer. That's all I can say so far. Okay. Okay, but anyways, if there are no more other questions, right? Okay, I want you guys to complete part C. I'll only give you guys about 5 to 6 minutes to complete this. Okay. About 1 more minute. Okay, let's just quickly go through this final part here because I want to move on to a longer question after this. Okay, so let's take a look at C part 1 now. Okay, they want you to draw the three of the bidentate ligands. Now, sounds pretty simple, which it actually is. Okay, but some of you guys may be wondering how it's chiral in the first place. Okay, even though we answered that in part 2, right? Okay, let me just kind of break it down. Okay, so we have to position the bidentate ligands 2 by 2 by 2. Okay, so perhaps, right, okay, we cannot do something like this, definitely. Okay, this is a very common configuration, okay, but it's not possible because you cannot put the last bidentate ligand together, right? Okay, you cannot have one over here, one over here. It just doesn't work like that. Okay, so they have to be side by side to each other. So if you start off like this, okay, you can have another one just like that. And then you have the last one like that. Okay, so all you need to do over here is just to fill in all the H's. Okay, something like this, and that will be your answer for this portion. Okay, just make sure your nitrogen is the one that's bonded to the central metal atom. Okay, not the hydrogen. Just make sure it's positioned correctly. Okay, so before I draw the second one, okay, they did say that this is both of these structures are enantiomers. Okay, so if this is an enantiomer, we are basically asked to draw the normal image and its mirror image. In other words, the second structure has to be the mirror of the initial structure. Okay, so again, some of you guys are asking me, right, how is this even chiral? Okay, because your own knowledge of chiral is in organic chemistry, right, where you have a carbon with 4 different groups. Okay, carbon with 4 different groups and all that kind of stuff. Okay, so clearly this isn't about carbon. Okay, it's looking at a slightly out of syllabus context of what an enantiomer is like in transition elements. Okay, but we will answer that shortly in part 2 now. Okay, but anyways, mirror image means okay, we have to draw the exact replica of this guy, okay, but the flip of it. So let's flip this around. Okay, so this part over here, oops, okay, this part over here, you flip it, he will end up over here now. So you have to position it strictly like this. Okay, you cannot just freely position these ligands. This one flip already end up on these 2 bonds. Okay, so let's throw that in. And finally, these 2. Okay, fill in all the H's. Okay, and that will be your answer for this portion. Okay, so just why they are enantiomers, right, is kind of because it's a bit hard to imagine they are enantiomers because they don't look like they look like 2D shapes, right? Okay, but they are actually not 2D structures. Okay, you have to really challenge your own intuition and realize that all these are actually 3-dimensional. These ligands are positioned over many planes, right? Okay, got the flat plane and then got the upper plane and the lower plane. Okay, so there's the ligands are positioned all over the place. Okay, so it's actually possible for this guy to be an enantiomer because in the second part of this question, they're asking for why is chiral, right? And all you need to do here, right, is to fall back on your fundamental definition of an enantiomer. Because 2 things. The number 1 thing is this complex here, right, has non-superimposable mirror image. Okay, the mirror image is not superimposable on the normal image. And how do we know that? Is because remember the one ligand here, right? Okay, can be placed in so many different planes of this molecule. I know it's very difficult to visualize, okay, and you don't need to be able to visualize. All you need to understand is they are positioned across different planes. So when this molecule is flipped in the mirror image, it is not superimposable on itself. Okay, so that is the fundamental requirement for an enantiomer to exist. Okay, and you can also mention the second criteria, which is that there is no internal plane of symmetry in this molecule. Okay, this complex is not symmetrical. Now, from first glance, right, it does look symmetrical because there are it really does look symmetrical, right? Okay, but you have to understand yet again that this is a three-dimensional shape, so it's actually not symmetrical. Okay, so you can mention, in fact, I think if you mention any one of these, you can get the mark already. Okay, but next time just answer the question based on your own knowledge. All right. Okay, and part 3 actually must know, okay, because we talked about properties of enantiomers quite recently also, okay, and they want physical properties. Okay, so remember, when it comes to physical properties, right, enantiomers have the exact same physical properties, not even similar, exact same. Okay, so stuff like boiling points, melting points, or density or solubility, whatever. Okay, all these physical properties, you can just mention one. They have the same boiling point, same solubility, whatever. However, there is only one exception, which I also discussed not too long ago, except for the direction of rotation, right? Direction of rotation of plane polarized light. That is the only exception to this rule, right? Okay, that's the difference. Okay, so that's the answer to this question. Okay, just remember, when it comes to biological properties, then they are different. Okay, enantiomers share different biological properties. Okay, that's also something I discussed before. Okay, so part 3 should be quite simple. Okay, it's just that part 1 and part 2 seem a bit weird because we have never seen a complex that's chiral before. Okay, but it is actually chiral because chirality exists beyond carbon atoms. Okay, in real life, right? Okay, there's more than just carbon atoms that are chiral. Okay, complex ions can also rotate plane polarized light if arranged properly as well. Okay, so that's it for part C. Okay, again, any questions, okay, you can feel free to ask. Okay, but if not, I want to proceed to the more important question for today. Okay, so once you're done, right, okay, can you guys go over to question 6? Okay, this is a long question. I'll split it into 3 parts. I want you guys to first do part A. Okay, part A, very content-based, not difficult part. Okay, again, I'll time you guys. And I think, right, I'm only gonna give you guys 5 minutes for this. Just 5 minutes for 6 part A. Okay, we shall start right now. Okay, or maybe 6 minutes. Okay, maybe 5 minutes is a bit short. Right. Okay, 1 minute left. Okay, time's up, right? Now, I didn't give that much time for this question because I don't think it needs it anyway. Okay, so very quickly, let's just finish this up. A part 1, electrophilic addition. Now, you don't need to write the title of this mechanism, just go and give me the entire mechanism, right? Okay, over here, nothing much. Okay, just make sure you try to answer. Okay, don't just make sure you got everything inside. All right, okay. Okay, all the arrows, partial charges, everything. Okay, again, when you draw your product, you have to assume Markovnikov's rule is in play. And in fact, you should be always assuming the major product is formed. Okay, because this equals bromine, right? Okay, just take note of the second part. Okay, the second part, there is this additional step where you need to show how the additional H is being removed. Okay, so it's being removed because it's attacked by the Br minus. Just make sure that is shown in your answer as well. Okay, charge, positive charge on the oxygen. This is a textbook mechanism. Like literally, it can be found in your notes. Okay, so you shouldn't be getting this wrong. It should be just like 3 marks. Okay. Right, in the meantime, let's solve for part 2. Okay, for part 2, synthesis, we haven't done synthesis in a while. Okay, so let's see whether we can do more today. Synthesis-wise, let's just recall what I told you guys about synthesis. Okay, always going to count the number of carbons first. Okay, we from 4 carbons drop to 3 carbons. Okay, that's already one very important clue. Okay, from 4 carbons to 3 carbons, there's a step down reaction, and we can already see the the biggest step down reaction, which is your iodoform test. Okay, this is eligible for iodoform test, so perhaps we can do that first. Okay, so perhaps, okay, once you undergo iodoform test, we will get a carboxylate salt. Okay, but then what's next? Okay, so somehow, right, this carboxylic acid group, right, has to leave because it is just gone at the end of the day. So how do we remove this carboxylate? Okay, do we know any reactions involving carboxylate salts? Not really, right? We are more familiar with reactions regarding carboxylic acids, not really carboxylate salts. So what we need to do first, right, is to actually turn this into a carboxylic acid, and then we can proceed from there. Okay, small little detail. Carboxylic acid, okay, what do we turn it into first? Okay, so first of all, carboxylic acid, if you want to remove it, right, the main way is still your reduction, right? Reduction can remove it into a primary alcohol, and successfully primary alcohol, you can dehydrate to turn it into an alkene. So that's pretty much the answer to this question. Okay, so that's that. Okay, and then at the bottom here, yeah, okay, your reagents and conditions. Take note, this first step over here, iodoform test is always done in alkaline conditions. But okay, you want it to be protonated again so that you can reduce it afterwards. So you must follow by H2SO4, the most important part in this answer. Okay, next is reducing agent and this two. Okay, so remember that for dehydrating agents, most common one is this one, but we can also use EL2, 3, and heat, okay, depending on which one you guys chose. Okay, both are acceptable. Okay, so very basic organic questions here. Okay, that's why shouldn't take very long to solve. Okay, and we're going to slowly up the difficulty as we proceed on into the question. So what I want you guys to do now, I'll leave the answer here. Okay, but in the meantime, I want you guys to now try part B. Okay, part B, I'll give you guys a bit more time because I want you all to make sure your 5 marks you all can get it, because there's quite a lot of things to explain for part 5, like quite a lot. Go and read the question carefully. Okay, so I'll give you guys about 8 minutes. Okay, and go and properly write a nice answer for part 2 also. Okay, just complete the rest of part B. Give you guys 8 minutes. Okay, in the meantime, I will still leave this here. Okay, down to the final minute. Okay, time's up. Okay, so yeah, we just have these two parts. Okay, let's go over the answer. All right, talk about part one first. Okay, dot and cross diagram SOCl2, right? Okay, first things first, go and identify what is the central atom. Central atom here can only be sulfur. Okay, because again, the central atom should always be the one, right, that forms the most number of bonds. Okay, chlorine can only form like one bond, oxygen can form two bonds. Okay, but sulfur can form two bonds, but it can also expand as octet. Okay, so sulfur usually should be in the middle, and then you should surround the rest around sulfur, something like that. Okay, and then what you can do first is to settle all the number of valence electrons. Chlorine can only form one bond, so very quickly. Same thing here. Oxygen can form two bonds, so just draw a double bond here. Okay, and finally, go and check your central atom. The central atom sulfur must have 6 valence, so you still have another 2 more. Okay, so at the end of the day, you can get yourself something that looks like this: 3 bond pairs, 1 lone pair, trigonal pyramidal, 107 degrees. Okay, 1 mark for the shape and bond angle, and 1 mark for the structure. Must be able to secure this mark. Okay, not difficult at all. Okay. Now, I want to talk about part 2 because part 2 has a lot of moving parts, and I want to just tell you guys what is expected, how you should be structuring your answer and whatnot. Okay, so perhaps I can just show you guys the answer key also. But here, right, okay, they're saying that there are 3 different pH values when you add water to these 3 different structures. So clearly here they are asking about acidity. Okay, you're meant to rank and assign which structure gives which pH value. Okay, that's probably going to constitute a mark. Okay, another one would be the silver nitrate portion. Okay, so if you look at this question here, there are 2 parts. First, you must justify the different pH values. Okay, let's do that first. Okay, over here we have 3 different species. Okay, we got G, H, and J. Okay, H is the one with the additional chlorine. Okay, J is an acyl chloride. Okay, perhaps I want to talk about acyl chloride first. Okay, since this guy is the odd one out. Okay, acyl chlorides are, by the way, they are not acidic compounds. Okay, I repeat, acyl chlorides are not acidic functional groups. Okay, reason being, they do not have a H on the functional group to dissociate into H+. Okay, if you look at a carboxylic acid, if you look at a phenol, for example, they have H, so they can dissociate their H+. Right, okay, so when we think of acidic functional groups in our organic syllabus, okay, you guys can probably only think of like 3, right? Okay, alcohol, which is honestly not very acidic, phenol, and carboxylic acid. We never really mentioned acyl chloride. But how come acyl chlorides also produce acidic solutions? Okay, it's not because they are acidic in itself, but it's because of a reaction that they undergo with water, right? Okay, when they add water, this guy will undergo hydrolysis first. Okay, and this hydrolysis reaction will produce HCl. This is actually the main reason why you get an acidic solution, because HCl is once again a strong acid, right? He is the reason why acyl chlorides are acidic, considered so-called acidic. Okay, so you must tell me this, and of course, because it's a strong acid, he's the one that has the pH of 0.5, the lowest pH of the 3. Okay, so that is very quickly get it over with first. Okay, the second one is between 2.5 and 3. So you look at these two, they're both carboxylic acids. Okay, so this has now turned into an acidity question. Okay, acidity question. Okay, now clearly we are going to discuss about Cl. Okay, this guy is an electron withdrawing group. Okay, disperse the negative charge in stabilize the conjugate base. This guy here is the stronger acid. And G. Okay, stronger acid, so he's the one with pH 2.5. This guy is the one with the pH of 3. Okay, so that's how we should be assigning the values first. This entire part over here, right? Okay, with all these in mind, okay, hydrolysis to produce HCl is 1 mark. The electron withdrawing portion where you explain why it's a stronger acid, that's another mark. And the final mark, right, is to assign all the different pH values together. Okay, I'll show you guys the full answer later. Just going to explain the question first, okay, in a more simplistic manner. Okay, so that's the first half of the question. Okay, moving to the second part of this question, we now need to explain about the silver nitrate and the white PPT. Okay, of course, the white PPT here, you should know by now is AgCl. Okay, but they asked us to explain in terms of reactivity. Okay, so the first part of the question was acidity. Now they want you to explain reactivity, right? Okay, so reactivity of the organic compounds. Okay, what are we supposed to discuss here? Okay, so first of all, you need to first understand that only one of the solutions produce a thick white precipitate. Okay, and that one solution, as you can see, based on the word reactivity, we should know it has to be from your acyl chloride. Acyl chlorides are, after all, the most reactive functional group. But what are you supposed to compare this with? Okay, if you guys compare this against this, it is wrong. You shouldn't be comparing an acyl chloride versus a carboxylic acid. Remember, when you compare the reactivity of chlorine-containing compounds, we are actually comparing between J, acyl chloride, and H. It's not about the carboxylic acid here, but it's about this part of the molecule, acyl chloride versus alkyl chloride. Okay, very quickly, let's just explain this. This one has two highly electronegative atoms, so the carbon is highly electron deficient, very susceptible to be attacked by a nucleophile. Okay. Whereas for this guy here, not as susceptible because you only have one electronegative atom, so it's not as electron deficient, so not as susceptible. Okay, you should be discussing this. Okay, and then link it back to the AgCl precipitate. That is 2 marks. Okay, and let's take a look at the full answer. Okay, so looking at this here, okay, go and check your marks carefully. Okay, hydrolyzed in water, you must tell me HCl is the strong acid. You must, that's the reason why he's acidic. Okay, that's 1 mark. Okay, electron withdrawing all the way to explaining he's a stronger acid, there's another mark. Okay, you assign all the pH values correctly, there's another mark. Okay, and then the next part is quite demanding because they want you to explain the whole reactivity segment here. Remember, let me just highlight down the keywords. Okay, 2 highly electronegative atoms, more electron deficient, more susceptible to nucleophilic attack. It's the classic 3 steps to explain reactivity. Okay, and then I justified why and how the AgCl is formed. Okay, the Cl atom is liberated as Cl minus, okay, which then forms a white precipitate. That final part makes up your second mark. Okay, so 5 marks in total. Okay, so slowly go and check your answer. Again, any questions? Yeah. So far the question has been very conceptual driven. Okay, and now we're going to move on to that final part. Okay, we're going to do this last part and then we will take a break. Okay, so this last part I think is a very good question. That's the reason why I even cut out this whole question in the first place. Okay, very good question on this final part. So if anyone still needs this later, you can just tell me and I will show it. Okay, but right now I'm going to move on to part C. Part C is really well said, I think. Okay, that's what I gathered when I looked through all the recent prelim questions. So yeah, okay, I want you guys to try this entire part. I'll give you guys a bit more time because this part requires you guys to think a little bit more. Okay, so 8 marks over here, give you guys 12 minutes. More than enough time to do this question properly. Okay, so pace, you will have more enough time to complete this. Okay, so right, 12 minutes. Okay, we shall start now. Okay, final portion before we can take a break. Okay. Okay, we have about 5 minutes left. Okay, so that was 12 minutes. Okay, I'm gonna go over this question now. Right. Okay, I think this is a well set question as I said earlier. Okay, I will take some time to explain how this all works. Okay, then we'll slowly review the answers. Okay, so this looks like a very typical titration curve. Okay, it is similar in a lot of ways actually. Okay, but let's just explain how this setup even looks like first. Okay, so first of all, right, we have a solution just made out of Cl minus. Okay, and then we are titrating it with Ag plus. Okay. Of course, when we are titrating it with Ag plus, we are going to get AgCl precipitate. Okay, and this precipitate is going to change things a little bit, okay, in this setup. Okay, and we also have to understand why it kind of looks like a titration curve, like it looks like a normal pH titration curve. Right? Okay, so the setup here seems pretty simple. Okay, but when you add Ag plus, right? Okay, I hope you all also realize that the moment you add Ag plus, you're going to precipitate out AgCl solid. Meaning to say, the solution doesn't actually have that much Ag plus ions. Because the moment you add in Ag plus, it's just going to precipitate out with a Cl minus. Okay, and that kind of explains, right, why at the very beginning of the PAG is very high. Okay, again, what is PAG? Okay, PAG is the opposite of concentration of Ag plus. If PAG is very high, that means at the very start, there's very, very little Ag plus concentration, which makes a lot of sense because the moment you pour in Ag plus, it immediately leaves the mixture. Okay, when it leaves the mixture, that means how much that's actually swimming around in the solution here is very, very low. Okay, on the other hand, why is it that the PAG here is super low? PAG here is low because the concentration of Ag plus is high. Why is the concentration of Ag plus high? Because I need you guys to first understand, right, what does it mean for this reaction here to be at the equivalence point? Okay. Now, I've always emphasized that equivalence point implies that there is a complete reaction. Right? A complete reaction only means that your Cl minus is completely precipitated out of the solution. There's no more Cl minus in that solution. Okay, no more. Okay, and the point at which we achieve no more Cl minus is this amount over here. And the next thing you need to realize is the moment Cl minus is no more, you're only adding excess Ag plus. Okay, you're just adding Ag plus inside. And again, the moment you add Ag plus inside, right, it's not going to precipitate now because all the Cl minus has already been precipitated out. So any extra Ag plus that you throw inside, right, it's just going to swim around in the solution. That's why Ag plus concentration begins to increase at this point. Okay, so that kind of answers one of the parts really. Okay, but it's good to break down the question first, to break down the graph, understand it a little bit first, right? Okay, before we go ahead with the questions. Okay, so let's look at part one, right? Okay, in part one, they want us to look at the concentration of Cl minus in the water sample, in the original sample. How do we find this? Okay, again, you just did a titration curve, right? Okay, you just conducted a titration experiment, and we know that at equivalence point, this is the best way to find out how much Cl minus there is in the solution, right? Over here, equivalence point, I also always emphasize on the idea of 1:1 ratio. Okay, after all, Ag plus and Cl minus react in the 1:1 ratio. So when we find out how much Ag plus there is here, we can equate this to the amount of Cl minus, and we can divide by the volume of the water sample in order to find its concentration. Okay, so let's take a look at the answer here. Okay, this. The equivalence amount of Ag plus is the same as Cl minus because it's a complete reaction. Then you divide by its volume. Oh, okay, with this, okay, quite straightforward. Okay, and then the second part of this question, okay, just let me switch it back. Show that a precipitate will be observed when you add this amount of AgNO3. Again, this is a show question. Okay, you need to show that a precipitate is observed. Okay, so what does it mean for a precipitate to be observed? It means IP must exceed the KSP of AgCl, right? Now, you're not supposed to start your answer with this expression. In fact, you're supposed to end off your answer with this expression because you're supposed to prove that this is, okay, you're supposed to prove this expression. Okay, so let's see what we need to prepare in our answer first. To reach this stage, I need to have the concentration of Ag plus and the concentration of Cl minus, because I need both of this in order to find the IP and in order to find IP versus KSP. So one by one, you're working backwards to see what you need. So I need to find the concentration of Ag plus and Cl minus. Okay, so let's look at the question. Is the concentration of Ag plus just this amount over here? And is Cl minus just your previous answer over here? Okay, no, because I hope you also realize that over here, right, you're adding a certain volume of AgNO3. You're going to change the total volume of the mixture. So when the total volume changes, the concentration is going to change as well. Okay, currently this water sample over here is 25 cm cube, but you're adding 0.1 cm cube of Ag plus. The volume has changed, so you must change the concentration accordingly. How do we change the concentration? I remember telling you guys this formula, right? Okay, in order to find the final concentration, you must take the initial concentration and you multiply by the dilution factor. I told you guys about the dilution factor before. You take the volume over the total volume. This right here is important, dilution factor. So we're going to do that, right, for both Ag plus and Cl minus. Okay, so let's take a look. Ag plus, Cl minus. Okay, Ag plus, the initial concentration is this, is given to us in the question, but I'm only adding this volume of it inside. Okay, this is the total volume. This is the new concentration. It's way lower, okay, because you are now putting a small amount, a small volume in a very big mixture. Cl minus, on the other hand, doesn't change much because most of it is already Cl minus. You're diluting it only by a small little bit. Okay, so that's the new concentration. And we can now find the IP of AgCl. Okay, we just multiply these two values together. And then, of course, we end off our answer with IP more than KSP. We're supposed to prove this. Okay, so IP more than KSP. So that's how you can just tell me precipitate is formed. Okay, and that's how you prove this question here. So again, now you shouldn't even be starting with IP more than KSP at the start. In fact, I don't know how you're going to start with that, even if you did so. Yeah, okay, I have no idea how you will start with that without any calculations. Okay, so that is for part 2. Okay, that's how we can prove. Okay, so far. All right, so we're starting to build towards the important part, which is part 4. Okay, but let's go over to part 3 first. Okay, part 3 is not that much, okay, but I want to talk about the significance of the answer in part 3. Okay, the PAG at point E. Again, point E is the equivalence pH. Okay, they say it's 4.87. So I can just quickly change this to the concentration of Ag plus. And they want us to find the concentration of Cl minus. Okay, so working wise, it's very simple, right? You find the concentration of Ag plus first, you convert 4.87, and then you can just sub that into your KSP in order to find Cl minus. Okay, it seems quite straightforward. It seems like you're just subbing in values. But let's not just move on from that. I want you guys to understand why. Okay, why do we sub it into the KSP? Okay, because of. Okay, let's just come back here. I want you guys to realize at point E, which is what this question is discussing, we are at a 1:1 mole ratio, right? Okay, equivalence point is always about 1:1 mole ratio. Okay, complete reaction pretty much. So at this point over here, right, you can expect your Ag plus concentration to be roughly equal to the Cl minus concentration in the mixture. Okay, of course, right, ideally, at this point over here, you don't want to have any Cl minus in the mixture, right? I mean, that's why it's called the equivalence point. But again, that is never really how it works. There's always a very small concentration of Cl minus still remaining in the solution. So meaning to say, when you come back to this question here, yes, there's a very small concentration left, but the rest of it, okay, you see the initial concentration of Cl minus is this amount, right? This concentration here. But now you're left with this. Okay, so you have done quite an effective separation already. Okay, but there's always the small concentration left in the mixture. Okay, so ideally it's supposed to be 0 lah. Okay, but it's not. Okay, so that is the significance of this answer over here. All okay so far? Okay, just sub it into your KSP. Okay, but now let's talk about part 4. Okay, so part 4, right, is actually a question that is also applicable to why do acid-base titration curves also kind of look like this? Why is it very gradual at the start and then it goes very sharply towards the equivalence point? Okay, I know acid base, they have buffers and all that. Okay, but let's look at this context. Why is it gentle at first? And then why is it very steep towards point E? I've already kind of explained that at the beginning. Okay, it's very high over here because Ag plus is very low. Why is Ag plus very low? Because the moment at the beginning, there's still a lot of Cl minus. So the moment you add Ag plus, it's just going to be removed immediately as a precipitate. So is there going to be Ag plus swimming around in the solution? No, right? Because it's already forming AgCl. So that's why at the start, right, it doesn't increase much, it doesn't decrease much. Yeah, okay, it just doesn't change much. That's why the gradient of the curve is very gentle. Okay, then what about point E? How come it suddenly starts to become super steep when it passes through point E? Okay, again, it all boils down to the idea of complete reaction. At point E, right, okay, again, ideally, most, if not all of the Cl minus has left the solution. Most of the Cl minus has left as AgCl. So since there's no more Cl minus, any further addition of Ag plus is just going to end up swimming inside the solution. So that's why the concentration of Ag plus in the solution increases very sharply, very quickly. Okay, that's why the PAG drops very sharply as well. Because at this point, all of it has probably precipitated already. Okay, so let's look at the answer here. Okay, I split it into two parts. This first part, at the very beginning, it is immediately precipitated. That's the words that I've used to describe this. Okay, Ag plus doesn't change much, so the PAG also doesn't change much. Okay, but then when it passes through point E, I acknowledge the fact that it's sort of the equivalence point, right? So all the Cl minus, okay, has been precipitated out as AgCl. Okay, so if you add any further addition, okay, that's a word that I use. Okay, any further addition, any excess Ag plus that you add, okay, will just cause the Ag plus to increase because there's nothing to precipitate the Ag plus out of the solution. Okay, that's why it starts to drop sharply instead. Okay, can see how this works now. Again, this is not an easy question. Okay, but I hope you can use this question to kind of understand why these kind of graphs look like that. You kind of gain a better appreciation of this kind of graphs. Okay, that's for part 4. And then let's quick, I'll come back to this later on. Okay, and then we finish up part 5 first. Part 5, explain how the answer in C part 1, okay, we will link back to our workings in C part 1. If the water sample is NH3, okay, this one I feel that I'll have to draw a diagram, right, okay, for you guys to kind of see this a bit clearer. Okay, so let me paint you guys 2 scenarios. Okay, ammonia. Okay, again, the ammonia by now you should know, right? It's supposed to react with your Ag plus. Okay, ammonia can react with Ag plus to form the complex. Okay, again, I don't have to spell it out for you guys. You should know this by now. Okay, but you should have 2 different scenarios. Okay, let's look at the first scenario, a clean scenario. Only Cl minus. Okay, no contaminants, no ammonia, nothing, clean. Now, in this experiment, the clean experiment, I had to add in 21.6 cm cube of Ag plus. Okay, this is the ideal Ag plus you need, right, to get rid of all the Cl minus. Okay, so that is the clean scenario. Now let's look at the contaminated scenario, the contaminated situation. Okay, contaminated means the Cl minus must still be the same as before. I hope you all realize that. Okay, don't say that, oh, Cl minus is now less because there's Ag, there's ammonia inside. No, it's just contamination means extra. Okay, there's an additional small little bit of ammonia inside. Now we know Ag plus can now react with both Cl minus and ammonia, right? Okay, let's split this up actually. Cl minus requires the same 21.6 cm cube of Ag plus. Agree? Okay, the same amount of Cl minus still requires the same amount of Ag plus to completely react. But is that all the Ag plus you're going to be adding? No, right? Because you are going to have ammonia reacting with Ag plus also. So imagine this, let's just put in some fake numbers. Okay, we need like 5 cm cube of ammonia of Ag plus to react with the ammonia. in total, right, can you all see you're actually adding more Ag plus than necessary? Okay, in total, you're adding 26.6 cm cube of Ag plus. Again, these are just fake numbers. I'm just painting a scenario for you guys. Okay, the same Cl minus will still require 21.6 minimally. It won't be less than that. But because there's a bit of contaminants that will also react with Ag plus, it will just make your Ag plus more than expected. Meaning to say, this graph would have been not 21.6, but you have read 26.6, which is wrong, right? So since your volume of Ag plus is higher than expected, how does that affect your answer in part 1? Okay, let's go back to part 1, right? If this is a larger value, then clearly this is a larger value. And then if this is larger, your concentration will also be greater than expected. So that's the answer to this question. Okay, so perhaps you want to be very clear. The Cl minus is the same, but now you have an extra item inside. So you need more Ag plus. Okay, so that's the answer to this question here. If there's ammonia, I acknowledge there's a complex form. If you don't do that, I think you should be fine also. Okay, but it's good to acknowledge the complex. Okay, so the volume of Ag plus to reach equivalence point will be larger than expected. Okay, I think this is the word we're going to use here. Okay, so the answer will also be larger than expected. All okay with this? Okay, Ken? Okay, any questions? Okay, you can just ask right now. But overall, I think, yeah, this is a pretty important question, right? I think it's quite well said as well. Okay, go ahead and digest this question with, after some time. Okay, so any questions so far? Okay, if there are no questions, right, okay, we shall take a break first. Again, during the break, you can ask me a few things. Okay, but just leave the answers here. Okay, we'll take a break and then later on maybe we'll just try a short question, then we will be done for today. Okay, so I'll give you guys, we'll take about maybe a 7 or 8 minute break. Okay, we'll come back by like 3:45, right? Right, okay, we'll come back by 3:45. Okay, just go and take a break first. Okay, we've got a few questions. Okay, first question, can explain the gradual part at the end of the PAG curve. Okay, so okay, at the end, is it? Okay, so even though the question never asks us about the end, okay, I think it's good to understand also. Okay, so at the end, right, okay, it starts to slow down because the more Ag plus you are adding, right, okay, do you realize, okay, first of all, I need you to realize that this y-axis is a measurement of concentration, right? Okay, as you are adding more and more Ag plus, the volume of the mixture will increase, right? Okay, so as the volume increases, it's just going to get more and more diluted. Okay, that's why towards the end, it starts to increase, but slower. Okay, it starts to increase, it still increases, but a lot slower. Can you kind of see that? Okay, it only increases sharply at the beginning, because at the very beginning, this part over here, you had just introduced Ag plus. Okay, you had just introduced Ag plus into the mixture. But then towards the very end, when there's a lot of Ag plus already in the mixture, any further addition, right, is not going to show a very sharp change. Okay, compared to this part over here. Can you see that? Okay, next question. How to know if it's common ion effect or it also forms complex? Okay, so I assume you asked that because you identified part 5 is a common ion effect. Kind of confused what you mean by that. Ammonia, after all, is not an ion one, right? So it can't be a common ion, correct? A common ion effect, right, Okay, this question has AgCl, meaning you're adding another compound, right? Which is either Ag plus or Cl minus. So a common ion, right, could be AgNO3 because the common ion here is Ag plus. Another common ion could be NaCl because the common ion here is Cl minus. But you're adding ammonia. Ammonia doesn't have an ion that is shared between AgCl and ammonia, right? Okay, so from now on, I did tell you guys that ammonia has to form complex with Ag plus. That's the only way. Yeah, okay. Right. Uh, everyone back. Okay. Right. Once you're back, right? Okay, we are going to do one final question. Okay, I want you guys to do question 4. Just do question 4A lah. Okay, so yeah, okay, so I want you guys to do question 4A, and we shall take 7 minutes to do this question. Okay, about there, right? So right, we can start now. Okay, about 1 minute left. Okay, come. Let's go over this synthesis. Okay, it's quite a huge one. 7 marks and quite a bit of steps. Okay, so we start off as a very simple molecule, right? But it somehow becomes this very large molecule at the top. Okay, but the main thing to identify first is let's approach it this way. Okay, why not, right? Okay, we just remember what we always did for reaction synthesis questions. Okay, and after doing that, okay, then we try to figure out what this compound B is. Okay, let's not go on a wild goose chase, right? Just trying to guess structure B. Okay, you might end up guessing correctly, good for you. But if you can't, then clearly, okay, we should follow our systematic procedure here. Okay, tartaric acid, 4 carbons. Remember, the first thing to do is always count the number of carbons. Okay, 4 carbons and ethene only has 2 carbons. So clearly there is a step-up reaction. And remember what we mentioned about step-up reactions? There's only one thing, okay, that can step up compounds, which is your nitrile. Okay, only nitrile is capable of stepping up. And there are only 2 ways of adding nitrile to the compound, right? It's either nucleophilic sub or nucleophilic add. Now remember, you only use substitution, right? If, okay, this is the second part of the process. When do we use sub and add? Sub is only if the number of functional groups are the same. But nucleophilic add is if the number of functional groups increase. So let's see here. We start off as ethene with only 1 functional group. But here, we have 2 functional groups. Okay, now the other side is just a duplicate. But yeah, so you can see there's an increase in number of functional groups, meaning we should be using this and not this. Okay, we need nucleophilic addition to happen somewhere in this process. Okay, so the thing is, when it comes to step up, a lot of you guys actually first assume nucleophilic sub, but that isn't the case for this question. We need nucleophilic addition, so we will probably have to find a way, right, to turn this into a carbonyl first. Okay, we have to turn this into a carbonyl. Okay, so how do we turn an alkene into a carbonyl? Okay, so let's just begin this. An alkene into a carbonyl. Can we do it in 1 step? Definitely not, right? Okay, it's not possible to turn it into 1 step. But, okay, we are supposed to try to turn it into this compound B, which is said is C2H2O2. Okay, so at the moment, what we can confirm is that there has not been any step-up reaction leading up to compound B. So meaning to say we can also infer, right? Okay, now that compound B has oxygens, we could use this to infer that compound B could be the aldehyde. Because if you read or the ketone, right? Okay, the carbonyl. Because from C and tartaric acid, right? Okay, we know the step-up reaction has to have already taken place somewhere here. Okay, the step-up reaction, I repeat, this step-up reaction has to be here and not this part. This first part, there are still 2 carbons. So let's separate this synthesis into this as the first part, and this is the second part. Okay, so let's try to settle this first part. How do we turn it into, how do we add oxygens? Okay, the only way we can think of adding oxygens to alkenes is either oxidative cleavage or mild oxidation. Now, oxidative cleavage is going to step down. We don't want to step down. So we can only mild oxidation here. Mild oxidation will turn it into a diol. So that is my first compound. I mean, that's the only way to start adding oxygens. Okay, But then you notice, right, we have a little bit too many of hydrogens. Okay, and we only have 2 hydrogens in compound B. And again, right, we are working towards this nucleophilic addition. We need to turn it into a carbonyl. Okay, so I'm going to turn this into a carbonyl, and it is possible because these are primary alcohols. We can turn this into aldehydes. And that is compound B. Again, you shouldn't be guessing compound B, drawing many different variations and iterations and whatnot. Okay, it's just going to waste time. Okay, this should be the procedure you're supposed to follow. Okay, especially step-up reactions, right? Okay, makes your life a lot easier, a lot streamlined. Okay, but since we have gotten that as compound B, we can move on to step 3. Okay, compound C, and then after compound C, we have step 4 to turn it into tartaric acid. Okay, so tartaric acid, right, as you can see, has a carboxylic acid and OH. Okay, but we still haven't done our step-up reaction yet. So quite clearly, right, the step-up reaction has to be in step 3. Because now that we have a carbonyl compound, we can undergo nucleophilic addition. So this is what it will turn into. Okay. And now our compound has 4 carbons. And finally, I can turn the CNs into carboxylic acids. So that is the full synthesis path. Okay, let's look at the reagents and conditions. Okay, first step, mild oxidation. So something like this. Okay, just make sure you use coal. Use NaOH or H2SO4, both are acceptable. Second step, okay, so you have to turn it into an aldehyde. Okay, please ensure you control the oxidation. Must use dichromate and you must heat with distillation. Okay, step 3 is the nucleophilic addition. Okay, remember it's cold, not heat. And then step 4 is your acidic hydrolysis, H2SO4 heat. 7 marks, 4 marks for reagents and conditions, 3 marks for your structures. Okay, Ken? Okay, so that is the synthesis here. Okay, there's a lot more to the synthesis than it initially looks up. Okay, because we have to follow or just follow whatever we already know. Okay, standard protocol. Okay, step-up reaction, you only have these 2 things to consider. Okay, consider the functional groups. From there, you already know it's nucleophilic addition, and then they give you a clue. Okay, the step-up reaction happens only after structure B. So this entire first half here, don't even have to care about that yet. Okay, your job here is to try to get yourself a carbonyl compound, because I know, okay, I will have nucleophilic addition taking place. Okay, without this initial knowledge, right, okay, it's going to be quite challenging to even start actually. Okay, Ken? Right, it's been a while since we did synthesis. Okay, so there are some questions in this worksheet that help you practice that. Okay, and if there are no questions, right, okay, that's about it for today already. Again, the first 3 questions are all 2018 older questions. Okay, but again, just go and do the next couple of lessons. I will include a mix of both, right, both old questions and new questions alike. And we'll be focusing only on the new questions. Okay. Okay, again, any questions you can stay back and ask. Okay, if not, that's about it for today. Those attending the 4:30 class, you can leave this Zoom also, because I'll be creating a new Zoom link. Right. Right, thank you.
Kai Xiang.
Yes.
I have a question, it's not related to the questions.
Yeah, sure.
Like for solubility, right? Solubility, sorry. Then if they give you CaIO3 2,
Okay.
then you write the equation, then it will be 2IO3, right? Minus.
2IO3 minus, yes.
Then after that, if you want to calculate like KSP, and then you found concentration of IO3, can you just divide it by 2 to get concentration of Ca2 plus?
Okay, I'm assuming that the question also mentioned saturated solution.
Yeah.
Right, so like this. Okay, so if let's say they said, right, yeah, the solution is saturated. Okay, so this is S, this 2S. So if you have the concentration of IO3 minus, provided they say it's a saturated solution, then yes, you can divide by 2 to find the solubility of the salt. Or calcium 2 plus, yeah, same thing.
Okay. Thank you.
Yep.
Okay, thank you. Bye-bye.
Right, bye.
I also have a practical question. For geometric titration, right? Is it the total volume of the reactions has to be the same?
Wait, the first part you were a bit soft, so I missed the first part.
Oh, for like geometric titration, like the one where you add different proportions of acid and alkalines.
Geometric titration.
Geo-
Iodometric titration.
No, okay. Is the energetics part where you add different
Oh,
proportions?
thermometric titration.
Yeah.
Oh, okay, yeah, wait.
Is it the total volume still have to be the same, or can it be different?
Okay, I've seen both. Some experiments, right? They continue adding, like they add a bit. So progressively they keep adding, right? So that means the volume here will just keep increasing. But I've seen another type of thermometric titration where they ask you to not just keep adding progressively, but they keep asking you to set up a new, set up a new mixture. So they keep the volume of the mixture constant, but they vary. Okay, so maybe I'll just write it down now. Okay, so I've seen some experiments where they have FA1, FA2, and then they try to keep the total volume at like 100 cm3, for example. So the first experiment, they use 50, 50, then 60, 40, then 70, 30, something like that. Basically, they keep they set up different reaction mixtures. Okay, like 3 different reaction mixtures or more than that. Yeah, but then there's also the other type, right, where they add progressively. They add 5 cm3 progressively, and then they keep taking the temperature every time they add the small addition. So it could go both ways. It depends on the nature of the question also.
Oh, then in what situation will we use the second one? Or is it like
Progressive addition one, is it?
yeah?
Honestly, I've seen a mixture of two. There's no indicator to say which one is used for which. Mostly acid-base reactions, right? Like pure acid-base reactions, they will tend to have the progressive addition. But again, it could go both ways.
If you have the progressive addition, is the temperature will keep on increasing the more you add it until endpoint, right? Then it will decrease.
Yeah, until the endpoint, and then after the endpoint, it will start to cool down the mixture. Yeah.
Okay, thank you.
For that question, right, will the graphs be different, like the shape?
No, won't be different.
Oh, so it'll be like the cross.
Yep, it will be this.
But sometimes like the downward side is like less.
Sometimes they do this, right?
Yeah,
Right.
it's kind of like a thing.
Oh wait, you're saying okay. Sometimes I see the downward side is a straight line. The straight line one, right? Okay, applies for mostly solids, because if you add additional solid, right, the solid is not gonna cool down the mixture. It is very situational. Okay, because I've seen one experiment where, okay, let's talk about this first. The reason why it cools down afterwards is because usually you're adding an aqueous solution, and then it's going to cool down the overall reaction mixture, right? Yeah, okay. But then this scenario, right, it's a very specific scenario in which they actually use this thermometric titration experiment to find the percentage purity of a solid. Okay, so they use this to find percentage purity. Okay, like beyond the equivalence point, right? Why the temperature doesn't drop is because you're just adding more and more solid. But at the end of the day, right, let's say the percentage purity is 80%. No matter how much that is, right? Okay, only a fixed amount of solid is reacting. solids can't really cool down the mixture. Okay, I've seen answer keys that are like this, right? But if they ask you guys to draw a graph, I suggest you all just stick to this. Okay.
Okay, thank you.
You.
Yep.